Welcome back, everybody, to another deep dive. This time we are taking a look at state space models, SSMs for short. And, they're this mathematical framework that pops up in all sorts of fields, like robotics and AI and ecology and even finance.
Yeah, it's fascinating because all of those fields are kind of relying on this underlying idea of understanding how things change over time. Almost everything we interact with is kind of a system in motion in a way.
That's a great way to put it.
Yeah.
And, for this deep dive, we've got academic papers, robotics manuals, we've got science articles, even a YouTube video about animal tracking. So clearly these SSMs are a big deal. So our mission today is to really try to break down what they are, why they are useful, and maybe uncover some surprising applications along the way.
I think that's a great plan. And, at the core concept of a state space model is surprisingly intuitive. Imagine you're trying to predict where your car will be in 5 seconds. You'd need to know its current speed, its direction, maybe even if you're braking or accelerating. And that's essentially what SSMs allow us to do, but for much more complex systems.
So instead of just sort of like guessing, we're actually using math to model the system's behavior.
Exactly. And, the Introduction to State Space Control documentation from First Robotics does a great job breaking down the components of an SSM. They use these things called matrices, which sound complicated, but it's just a way to organize the information.
Okay, matrices. I vaguely remember those from high school. Help me out here.
Yeah, so think of it like this. You've got your system matrix, which describes the system's inherent behavior, like how a pendulum naturally swings back and forth. Then there's the input matrix, which represents external factors, like if you were to give that pendulum a push.
So it's not just about what the system is doing, but also how we can influence it.
Precisely. And the output matrix tells us what we can actually measure or observe about the system. Like, we can see the pendulum's angle, but we might not directly see the forces acting on it.
Gotcha. Okay, and what about that feed-through matrix thingy?
Yeah. The feed-through matrix is for when an input directly affects the output without changing the internal state. So it's like if you hit a drum, the sound is immediate even though the drumhead's vibration is part of the internal state.
I see. Okay. I'm starting to see the framework here. But why go through all this trouble to model systems? What's the payoff?
Well, the beauty is that this framework, it can handle both continuous and discrete systems.
Yeah.
So like a robot arm moves in steps while a pendulum swing is continuous. SSMs can model both.
Okay, so a universal language for change. I like it. Now, I kept seeing this Kalman filter mentioned in our sources. What's the big deal with that?
Yeah, the Kalman filter is kind of a star algorithm built on SSMs. It basically helps us estimate a system's true state, even with noisy data. So think about GPS. It uses a Kalman filter to estimate your position based on satellite signals, which can be unreliable.
So even if my phone thinks I'm driving through a building,
Yeah.
the Kalman filter is kind of keeping me on track?
Yeah. Exactly. It combines our imperfect measurements with the system model to give us a more accurate estimate. And it's been around for a while. According to the Wikipedia article, it was actually developed in the 1960s and even used in the Apollo program for spacecraft navigation.
Wow. From Apollo missions to helping me find the nearest coffee shop, that's quite a legacy. But what about systems that don't behave in a simple linear way? Like the pendulum example in the robotics documentation showed how things can get complicated.
Yeah, that's true. That's where things get even more interesting. We have to adapt the standard Kalman filter for those situations.
So what do we do when the system throws us a curveball?
Well, techniques like the extended Kalman filter and the unscented Kalman filter come to the rescue.
Unscented. That sounds intriguing. And maybe a little dangerous.
It's a powerful tool, trust me. Instead of forcing a linear approximation, it uses carefully chosen sample points to represent the system's uncertainty more accurately, kind of like if you were trying to map a curvy coastline. You'd use multiple measurements to get a better representation than just drawing a straight line.
I see. So it's about adapting to the system's complexity. Speaking of adapting, that YouTube video from Neon Science showed a completely different use for SSMs, estimating animal populations.
Right. Isn't that fascinating? They're using SSMs for mark recapture studies, modeling things like animal survival and capture probabilities to get a better grasp of population size.
So these same models can help track spaceships, A&D estimate squirrel populations. I'm already sensing the versatility of SSMs. So what else can they do? It feels like we've only just scratched the surface here. Give me more. Where else do these SSMs shine?
Well, think about robotics. That first robotics documentation really emphasizes how SSMs are key to designing sophisticated control systems.
Yeah.
They allow us to create algorithms that guide robots smoothly, precisely, even adapt to changing conditions.
So it's not just about understanding what a robot is doing, but actually telling it what to do. That's pretty amazing.
It is. Imagine like programming a robotic arm to pick up an object. SSMs give us the tools to actually design that control strategy, making sure it moves smoothly, doesn't overshoot, and corrects for any unexpected disturbances.
It sounds like SSMs are really the brains behind the operation. Is this kind of control limited to just robots, though?
Not at all. Remember that Wikipedia article on Kalman filters? It mentioned applications and navigation systems for aircraft and submarines. They rely on SSMs and these filtering techniques to stay on course even in unpredictable environments.
So we're talking about guiding planes through the air
Yeah.
and submarines through the depths of the ocean, all thanks to SSMs. It's like they're the unsung heroes of modern technology.
Absolutely. But it's not all about machines either. Remember that Neon Science video with the animal tracking? They were using SSMs to model ecological systems, like how diseases spread or how populations fluctuate over time.
It's incredible how these same mathematical ideas can be applied to such different areas, from robots to submarines to ecosystems. It's a bit mind-boggling.
It really speaks to the power of a good mathematical framework. You know, SSMs provide a way to understand how things evolve, regardless of whether it's a mechanical system,
Yeah.
a biological population, or even potentially financial markets.
Okay, now you're really getting me curious. Is there anything SSMs can't do?
Well, there are limits, of course, but their potential is vast. You know, we haven't even touched on state space search yet.
State space search. That sounds intense. Like searching for a lost sock in a parallel universe?
Not quite, but it does involve searching through a space of possibilities. That Geeks for Geeks article explains it well. Imagine you're trying to solve a maze. Each intersection is a state, and each path you can take is an action. So state space search is about finding the right sequence of actions to get from the start to the finish.
Okay, so it's like mapping out all the possibilities and then finding the optimal path.
Exactly. And there are different algorithms for doing this, like breadth first search and depth first search, each with its own strengths and weaknesses depending on the problem. It's like choosing the right tool from a toolbox.
Gotcha. I'm starting to get the idea. So how do SSMs fit into this whole search process?
Well, often they work hand in hand. SSMs provide the model of how the system behaves, and then state space search uses that model to explore potential solutions. It's like having a map and a compass to navigate through a complex landscape.
Okay. This is all incredibly fascinating, but I have to admit, I'm feeling a bit overwhelmed. Can we bring it back down to earth with a concrete example?
Sure. Let's go back to robotics. That Introduction to State Space Control documentation mentions something called the linear quadratic regulator, or LQR for short.
LQR rings a bell, but I need a refresher.
Essentially, LQR is a control algorithm that leverages SSMs to design optimal strategies. It's about finding the best way to control a system while minimizing a certain cost.
Cost, like how much electricity the robot uses.
It could be that, but also things like how quickly it reaches its target, how much fuel it consumes, or how much error there is in its movements. LQR is about finding that sweet spot, balancing performance with efficiency.
So it's like finding the most scenic route that also uses the least amount of gas. I like that.
Exactly. Imagine designing a self-driving car. You could make it prioritize speed, but it might be jerky and burn a lot of fuel. Or you could focus on fuel efficiency, but it might be slow to accelerate or brake. LQR helps you find the right balance.
Okay, so it's about trade-offs. Is there a way to adjust that balance?
Yes. LQR lets you fine-tune the system's behavior. You can adjust the emphasis on different factors in that cost function. Think of it like adjusting the bass and treble on a stereo. You're tailoring the performance to your specific needs.
That's amazing. So you could create a robot that's super precise,
Hmm.
even if it uses a bit more energy. Or one that prioritizes efficiency over speed. It's like choosing the robot's personality.
I love that analogy. And that's exactly what the first robotics documentation highlighted. By tweaking these things called the Q&R matrices in the LQR algorithm, you can dramatically change how the robot behaves.
Okay, that's seriously cool. I'm starting to see why SSMs are such a big deal. They're not just about modeling what is, but also influencing what could be. This deep dive has taken us from spaceships to squirrels to self-driving cars, all thanks to the power of state space models. It's been quite a journey.
It really has. It highlights how, a seemingly abstract mathematical concept can have such tangible and far-reaching applications.
Exactly. But before we wrap up, I'm curious, where do you see this all going? What are the frontiers of SSMs?
That's a great question. And one that researchers are actively exploring. We've seen how SSMs can model physical systems, biological systems, even some aspects of economics. But what about social systems? Could we use these models to understand or even predict things like trends in fashion, the spread of ideas, or even political movements?
Whoa, now that's a thought-provoking idea. It's like trying to model the collective behavior of an entire society. Is that even possible?
It's certainly a complex challenge, much more so than modeling a robot or a pendulum. Human behavior is inherently unpredictable, influenced by countless factors and feedback loops.
But theoretically,
Mhm.
if we could capture enough data about social interactions, cultural influences, economic trends, and so on, could we build an SSM that represents society as a whole?
That's the million-dollar question. And even if we could, it raises all sorts of ethical considerations. Would we want to predict human behavior on such a large scale? What are the implications for individual freedom and societal control?
Yeah, those are some deep philosophical waters we're wading into. It's like that age-old debate about free will versus determinism. If we could predict the future of society, will we be shaping it or simply confirming its inevitability?
Mm. It's a fascinating and complex issue, and one that I don't think has an easy answer, but I think the fact that we're even having this conversation is a testament to the power and potential of state space models. They've come a long way from guiding spacecraft to potentially modeling the very fabric of our society.
It really is mind-blowing to think about. So as we wrap up this deep dive, what's the key takeaway you want our listeners to walk away with?
I think it's this. State space models are more than just abstract math. They're a powerful tool for understanding and interacting with the world around us. From the simple to the incredibly complex, whether you're an engineer, a scientist, or just a curious individual. Understanding the basic principles of SSMs can give you a new lens through which to view the intricate workings of our universe.
Beautifully put. A huge thank you to you, expert speaker, for guiding us through this fascinating landscape of knowledge. And to you, dear listener, keep exploring, keep questioning, and keep diving deep. Who knows what other mysteries await us in the vast ocean of knowledge? Until next time, happy modeling.